Hello dear students, in this video we will discuss about the rate equation for zero and first order reaction. Firstly, we will do the rate equation for zero order reaction. So firstly, let us consider a zero order reaction. Reactant gives product. Now, the concentration of the reactant, we know it decreases, but the concentration of the product increases. So, the concentration at time 0, let us consider that the concentration of A at time 0 is A and concentration of product is 0. Now, concentration at time T, let the time be T. We know that the concentration decreases. Initially it was A, but with decrease in concentration it becomes A minus X. And concentration of the product increases from 0 to X. Now let us represent the rate in terms of differential rate equation, which means in terms of differentiation. Now it is the change in concentration with respect to time. We know that for zero order reaction, it is rate constant, concentration of the reactant for zero order reaction. Now this very equation can also be written in this form. We know that power 0 means this entire term is equal to 1. So this very equation can be written as dx is equal to k dt. Now we will go for integrating this equation. Integration of this equation, integration of dx is equal to integration of k dt. We know that k is a constant term, so it will be out of the integration. So this very equation can be written as integration of dx is equal to k integration of dt. Now integration of dx can be written as x and integration of dt will be t. And upon integration we always write a constant term. Now at t is equal to 0 and x is equal to 0, this very equation can be written as 0 k, since t we are taking 0, plus c. So we get concentration, the constant term as 0. So x is equal to kt. That means we got the constant term as 0 upon taking t is equal to 0 and x is equal to 0. So upon getting constant term as 0, this very equation can be written as this way. Now this is the required integral rate expression for zero ordered reaction. Also for a zero ordered reaction we got this. So this can also be written as k is equal to x by t. Now this x is equal to initial concentration minus final concentration of the reactant. So in place of x we can write k is equal to initial concentration of the reactant minus final concentration of the reactant divided by time. You have to remember this equation as well as this. Let us now do the rate equation for first order reaction. Let us consider a first order reaction. Concentration at time 0, that means the initial concentration of the reactant is A and initial concentration of the product is 0. At time t, with the passage of time, the concentration of the reactant will decrease. So the decrease in the concentration of the reactant is given as A minus X and increase in the concentration of the product is given as X. From A it is decreasing to A minus X at time t, and from 0 it is increasing to x at time t. Now representing in terms of differential equation dx by dt, constant with the decrease in the concentration of the reactant, first order reaction. So this very equation can be written as dx, this will come to the denominator, k dt. Now upon integrating, constant will come out, dt. Now if you remember the log formula, this is in the form of dx. So this will be written as, now integration of 1 by a minus x dx is log a minus x, differentiation of a minus x. So log a minus x, d by dx of constant term is 0, so this will be cancelled out. D by dx of x is 1, so from here we get minus sign, so it will be minus 1. So this equation will become log of a minus x, or it can also be written as log ln a minus x. So this, after differentiation and integration, we are getting this value. So we can write minus ln a minus x is equal to k, integration of dt will be getting t plus constant. Whenever after integration, we will always put a constant term. Now at time 0 and x 0, this very equation can be written as ln a minus 0 k 0 plus c. So this will be 0, this will also be 0. So from here we get log a is equal to c. So concentration we are getting as, or constant, not concentration, constant term we are getting as minus ln a. So this equation now can be written as minus ln a kt. Instead of this constant, we already got the value, so we will write down ln a. This very equation can also be written as kt is equal to, this will go to the right hand side, ln a minus ln even it can be written as since this is a minus term, from here it can directly be written as ln a divided by a minus x. I'm sure you have done this in your maths, so I don't need to explain it. So this ln, if we want to remove, I have explained this in chapter 2. ln, if you want to remove, you can write down 2.303 log instead of ln. So this very term can be written as kt is equal to 2.303 log a by a minus x. So from here we can also write this as t is equal to 2.303, k will come to the denominator, log initial concentration by the final concentration, because A is the initial concentration and final concentration is A minus X. So in place of initial A we can write A naught, and in place of final we can write AT. So this is the required integral rate equation for first order reaction. Now let us see the half-life period of a first order reaction. What does half-life mean? Let us see the definition. It is defined as a time during which the concentration of reactant is reduced to half of its initial concentration. That means the final concentration will become half of the initial concentration. That is what means half-life time or half-life period. In this half-life period, the final concentration will become half of initial concentration. Now we already got this value from the integral rate expression for first order reaction. By definition, it says that half-life period, that is T half, the final concentration will become half of the initial concentration. This is by definition. So this very equation can be written as the half-life period T half is equal to 2.303 K log initial concentration. Now in place of final concentration we can write this way. Now this very equation will become 2 initial concentration. This will get cancelled out. We will be left with this equation log 2. Now 2.303 K log 2 value we have 0.301. Upon multiplication we will get 0.693 K. So this is the half-life period for a first order reaction. Now from here the initial concentration is cancelled out. Initial concentration has no role to play in this very equation. So we can also say that half-life period for a first order reaction is independent to the initial concentration of the reactant, because the initial concentration gets cancelled out. It has no role to play in this very equation. That means this equation, the half-life period of a first order reaction is independent of the initial concentration. Now let us see what is pseudo first order reaction. These are those type of reaction which appears to be of higher order, such as second order, third order reaction, but are actually first order reaction. Let us see one example. Sucrose react with excess of water giving sugar. Now here water is in excess. That means 1 mole of sucrose is reacting with excess of sugar. Say 1 mole of sucrose is reacting with 1000 mole of water. Now here 1 mole will react with only 1 mole of water. So 1 mole reacts with 1 mole of water. How many moles are left? 9999 mole of water is left out. Now there will be no change in the concentration of water, but concentration of sucrose will change. There will be no change in the concentration of water. It will remain constant. Now logically it should follow second order reaction. Power will be 1. So it should follow second order reaction, but concentration of this is changing, but concentration does not change. It remains constant. So this will not participate in the rate. So here the order of this reaction will be just 1. So it will be first order reaction, not second order, because it is present in excess and its concentration is not changing at all. so it will be first order reaction, but it appears to be a second order reaction, but actually it is a first order reaction. Same follows for this reaction. That means this is present in excess and this is present in 1 mole. So 1 mole will react with 1 mole of very compound. So there will be some leftover moles of this very compound. So here this reaction should be third order reaction, 2 plus 1 third order. But in the same way, this concentration remains constant. It does not change because it is present in excess and only 1 mole is being used. So there is no effect in the concentration. Concentration remains constant. So this will not participate. So the rate will be first order, not third order. So this is what pseudo first order reaction means. They appear to be of higher order, but they are actually first order reaction. With this we come to the end of chapter 4. Keep on practicing the numericals given. Those are very easy. If you find any problem, kindly approach me.